Okay, good evening, everybody. And welcome to another session of Organic Chemistry. In today's session, we are going to finish with chapter 4. And of course, before we start with chapter 4, I just have a few announcements. On Monday, there will be another review session. That is at 8 p.m. So I will send you a reminder. I will send you a reminder on Monday morning. That is Monday, September 17th. And of course, on Tuesday, September 18th, we are going to have the first class exam. Okay, also, I do want to remind you that our homework assignment is due on Sunday. That is September 16th at 11 p.m. Okay, so now let us, what I want to do here, before we start with chapter 4, I want to also do some problems on chapter 3. But before we do that, let me get one of you to read the topics for chapter 4 for us. Okay, Dwayne, go ahead.
Major topics / concepts, cycloalkanes and derivatives, nomenclature of cycloalkanes and derivatives, cis and trans stereoisomers of cycloalkanes and derivatives, conformations of alkanes and cycloalkanes, halogenation of alkanes and cycloalkanes, conventions for writing three-dimensional representations.
Okay, very good. And thank you. Okay, so those are the topics we are going to be discussing in chapter 4. Of course, the chapter 4 is primarily concerned with the chemistry of cycloalkanes. And as we told you the last time we met, cycloalkanes are very much related to the alkanes. But before we do that, let us do a few problems from chapter 3. And this problem I will take from the previous 1-hour exam so that you have an idea what these problems look like. And also this is the same set of problems we are going to use for the review session on Monday. Okay. Okay, let us see here. Who do I want to call on? Yes, go ahead. Name? Okay, go ahead. Read number, no, let's do 19. Okay, which of the following molecular formulas is a straight chain alkane? That should be fearless. Yes, go ahead, Paris. A. Okay, why do you pick A? A is correct, by the way. That is correct. Why? Okay. Okay. Because it fits the formula. It fits the general formula, right? Which is CN H2N plus 2, right? Okay, so that is the only formula here that fits the general formula. Very good. Okay, about 20. About 20. Let us see here. I want somebody from that side to read 20 for us. Go ahead.
Using the symbol I, write structures for ethanol-aldehyde, carboxylic acid, the primary alcohol enemy.
Okay, so this here we just want to remind you of some of the basic structures of the common classes of organic compounds. So here we want to use the generic symbol R to write the structures for each one of these classes of compounds. Ketone, aldehyde, carboxylic acid, primary alcohol, and amine. So let us start with the ketone. What would ketone look like? Yes, right? 2 R groups. Okay, attached to carbonyl.
with a double bond to the
Okay, very good. So this is a ketone. So this is something that you guys just have to recognize once you see them. Okay, how about the aldehyde?
It's the same thing, but it's a ketone.
The same thing except that you have hydrogen attached to the carbonyl. Very good.
It's not related.
Sometimes you may have an aldehyde in which this R could also be an hydrogen. Okay, that would be the smallest aldehyde. Okay, sometimes you may have an aldehyde in which this R could be hydrogen. Okay, how about carboxylic acid? Carboxylic acid. Okay, you have okay, double bond O, which is a carbonyl group. The double bond O is called carbonyl. Okay, carbonyl group is a carbon-oxygen double bond. You find that this group is this functional group is very common in organic compounds. So, for the carboxylic acid, you say it will be R with carbonyl attached to hydroxyl. Very good. Okay, so this will be a carboxylic acid.
So a carbonyl group is automatically a ketone every time?
No, because you have carbonyl in many compounds. You have carbonyl in carboxylic acid. You have carbonyl in aldehyde, so it doesn't have to be ketone.
Okay.
Mm-hmm. Okay, so this is carboxylic acid. Okay, how about the primary alcohol? Primary alcohol. What would that look like? R attached to? No. How do I know that's a primary alcohol? If you give me this here, if you give me this, how do I know that this R, this carbon here?
It's attached to one carbon.
Okay, so you have a CH2? Okay, exactly. So what you want to do here, in this case, you want to have the R attached to a CH2 to show that that is a primary carbon attached to an hydroxyl group. And that's a primary carbon, primary alcohol. Huh? No. Primary simply means that carbon, that carbon is only attached to one other carbon atom. Okay. Okay. The primary alcohol means that the hydroxyl group is attached to a primary carbon. Okay. Okay. So about amine. About amine, what would that look like? Nitrogen is very good. So nitrogen, for the amine, that would be R attached to a nitrogen. Okay, that would be an amine. This will also be an amine in which you have nitrogen attached to a nitrogen and another carbon atom. That will also be an amine, or you have in case in which you have the nitrogen attached to 3 carbon atoms. Okay, all of these are amines. Okay? Okay, so let us, since we are talking about classes of organic compounds, let us look at other classes of organic compounds. How about a nitride? Triple bonded to nitrogen. Okay, very good. That's a nitride. How about an ester? Ester. R group, carbonyl attached to oxygen, and that oxygen is attached to another alkyl group. Okay. Now, in the case of an ester, this R group, let's call this R prime. Okay. This R prime could be alkyl. It could be hydrogen. Okay. or it could be aryl. Aryl is simply meaning that we have this here. This is an aryl group right here. So for example, I could have this. That would be a specific example of an ester. Or I could have this. That would be another example of an ester, in which you have the carbonyl attached to oxygen, and that oxygen is also attached to some carbon atom. In this case, you have hydrogen on this other side of the carbonyl. Okay, so these are some of the common classes of organic compounds. So we are going to encounter most of these organic compounds as we go along during the course of this semester and, of course, next semester. Okay, now let us go back. Oh, before we do that, let me do one more problem on this. All of these questions are from the previous exam. Okay, let us do this. Okay, Valerie, can you read this for us?
Acetic acid has a higher pKa value than chloroacetic acid. What does this mean?
Okay, what does this mean? Okay, this is chloroacetic acid, and this is acetic acid. So if I tell you, as what we have there, we say acetic acid has a higher pKa value than chloroacetic acid. What does that mean? Yes, sorry. Exactly, excellent. That means that the chloroacetic acid is more acidic. Okay, so that means this is more acidic. Keep in mind, the lower the pKa value, the more acidic the molecule is. Okay, and of course this is less acidic. You see that exam was very simple, wasn't it? Right? What? I said that exam was very simple, wasn't it? Okay, now draw the conjugate base for each. Okay, what is the conjugate base for acetic acid? Okay, you lose a proton, right? You lose this proton, okay? So the conjugate base is when you the product that you obtain after the loss of the proton. So for acetic acid, the conjugate base will be this. Okay, and for chloroacetic acid, the conjugate base will be this. Because you have a formal charge of -1 on the oxygen because you have lost the proton, and as such, the proton leaves behind a pair of electrons. So now you have a formal charge of -1 on each one of the oxygen atoms. Now, before we do questions, the part C, I do want to give you a little bit of background information. Okay, part C says, draw resonance structures for both conjugate bases, which means this here and this here, and use bond polarity to briefly explain the difference in the pKa value. In other words, why is the chloroacetic acid more acidic than the acetic acid? Yeah. Now, anytime you have, okay, let us say acidity, factors affecting acidity. if I have this molecule here, which is acetic acid, of course I say it is an acid because it could lose the proton. Could lose this proton. Just do an arrow to show that the proton is leaving the pair of electrons behind. And so you obtain this molecule here. So you obtain the conjugate base plus a proton. Now the strength of any acid depends on the stability of the conjugate base. That's very important. Strength of any acid, strength of any acid depends on the stability of the conjugate base, Now keep that in mind. That is very important. Okay. If on the other hand, we have chloroacidic acid, we have this here. Okay, this. This is the conjugate base of chloroacidic acid. Now we say that chloroacidic acid is more acidic than the acetic acid. In other words, what we are actually saying is the conjugate base of chloroacidic acid is more stable than the conjugate base of acetic acid. So now we need to give an explanation as to why that is so. Okay, before we give that explanation, let us also give you another example. Let us say we have ethanol. Yeah, ethyl alcohol. We say ethyl alcohol could also act as an acid. In other words, we could lose this proton here. So what do we get? We get this. So we get the ethoxide, we call this ethoxide, being the conjugate base of the ethyl alcohol. We know that the pKa value for acetic acid is about 5. We also know that the pKa value for ethanol is about 18. So acetic acid is a lot more acidic than the ethanol. Now, if you take a look at the conjugate bases of both of them, the conjugate base from ethanol, from acetic acid, and the conjugate base of ethanol, you will find that we could stabilize this conjugate base with resonance. So in organic chemistry, there are two concepts that we use whenever we want to stabilize any kind of molecule. Those two concepts are resonance and inductive effect. So those are very important. Inductive effect Those are the two concepts we use to explain the stability of most organic molecules. So in this particular instance, take this out of the way first. Why is acetic acid so much more acidic than the ethyl alcohol? We say if you take a look at the acetic acid, the conjugate base, we could write the resonance structure in which we simply move this electron here to here, and therefore this goes here. Keep in mind that let us keep all of our electron bookkeeping straight. We had this here before. So now you have another resonance contribution to this conjugate base, which is this now. So in the case of acetic acid, we could stabilize the conjugate base with two resonance structures. On the other hand, if you take a look at the conjugate base of ethyl alcohol, can you write a resonance structure for this? Is it possible to write a resonance structure for this here? No. In other words, the electron here is localized on oxygen. On the other hand, this electron here could be distributed over these three atoms here, so which makes that molecule a lot more stable. Okay, so in this case, we use resonance to explain why acetic acid is much more acidic than ethyl alcohol. Is that clear? Okay. Now, how about in the case of the chloroacetic acid? What can we use to explain the reason why chloroacetic acid is more acidic than acetic acid? Okay, what can we use? Okay, if you look at both of them, this is acetic acid, and when it loses a proton to form the conjugate base, you get this. Now, taking a look at both of the conjugate bases, can we use resonance to stabilize the conjugate base from chloroacetic acid? Can we? Yes, right? The answer is yes, right? Because we could draw resonance. Sorry about that. We could draw resonance that will stabilize this electron on this oxygen over these three atoms here, just as we did here. So we could do the same. Move this electron here to form a double bond between carbon and oxygen. And when you do that, keep in mind that you've got to keep your valence. So you have to move this pi electron away. Okay, so therefore we have this. So we have another resonance structure. So both of the conjugate bases could be stabilized by resonance. So therefore, the question is, how do we explain the fact that we know that chloroacetic acid, we could measure it, is more acidic than acetic acid. what concept do we need to use to explain that? Very good. Inductive effect. In other words, we have to use inductive effect. And what does inductive effect mean? Inductive effect simply means pulling electron away. Okay? We are pulling electron away. So in this case, we know that chlorine is very electronegative, because the comparison here will be, if you really want to make a comparison, it will be between hydrogen and chlorine, right? Okay, we know that chlorine is a lot more electronegative than hydrogen. So what it's doing here, it is helping to draw electron away from this area to this side of the molecule, as a result of the fact that it is a lot more electronegative. So because you know that the carbon-chlorine bond is a very polar bond, which means that we are pulling electron away to this chlorine. And as such, the chlorine is also helping to pull electron away from this part of the molecule. And that is what we mean by inductive effect. And that is thereby stabilizes the conjugate base of chloroacetic acid. Okay, do you follow that? And that was the question that we have here. The question here is, oh no, this is the question here is, can somebody read C for us again? Okay, we've done that already, right? That's what we just did. In other words, we do the resonance structures. You know, we say draw the resonance structures for the conjugate bases from these two acids here, this conjugate bases here. We did that already. And then we explain that the reason why the conjugate base of the chloroacetic acid is more stable is because of the inductive effect from this chlorine. In other words, chlorine is pulling electron away to that side, thereby helping to pull some of the electron clouds from here to this side of the molecule. Okay, so that is what that question is asking you to do. Okay, is there any question before we go to, yes? Yes, the electronegativity of chlorine is about what is it? It's about 3, right? Compared to the electronegativity of hydrogen, which is about 2.1. So because you are comparing what we are doing here, comparing we are in essence comparing the electronegativity of hydrogen compared to chlorine. Okay, electronegativity of hydrogen is only 2.1, so it's not really helping to pull the electron away as much as chlorine does. Okay, so very good. So now let us go back to chapter 4 so we can finish chapter 4 today. Oh, by the way, on chapter 3 and 4, we are not going to do our confirmation, so there will be no question on confirmations in your exam, so we would defer those questions till the next exam. Okay. Okay. Okay, so now we know the topic that we need to discuss in chapter 4. Get my Okay, so we want to discuss the chemistry of cycloalkanes. Of course, you know this slide here simply gives you a list of learning outcome objectives, things that you should be able to do upon completion of this chapter. And I'm sure you also have seen this before, when we did alkanes. Okay, all of these, the names of these straight chain alkanes, you need to commit them to memory, because they will serve mostly as the basis for the nomenclature of most organic compounds. Seriously, you need to know them. Okay? Okay, so pentane is a C5 alkane molecule, hexane C6, so all of those things you need to know. Okay, so now, when we deal with cycloalkane, just as the name suggests, these are cyclic molecules. The name will be derived from the name of the corresponding alkane molecule. Okay, these are examples of some of the smallest type of cycloalkane. What you have here, when you have a cycloalkane, of course, this is a cyclopropane. This is telling you you have a 3-carbon molecule, which is in a ring system. Okay, so in essence, what you have is CH2 attached to CH2 attached to CH2, and then you have the ring system right here. So in essence, you could almost think of the alkanes. Supposing we have this, or the cycloalkanes. What is the name of that molecule? What is the name of that molecule? Butane, right? Okay, butane, good. Okay. Imagine that we simply come here. Imagine that we come here, we take one of these hydrogen out. We now have 2 here. And here, we take one of these hydrogen out. We now have 2 here. Okay? We need to fulfill the valence of carbon. So then what do? We simply join this carbon and this carbon. That, in essence, is what we have here. And that molecule that we obtain will be, the skeletal structure will be that. That will be cyclobutane. So what does that tell you about the general formula for the cycloalkanes? What would the general formula look like for cycloalkane? What is it? CN H2N. That 2 hydrogen is gone. So anytime you see a general formula that is CN H2N, it could very well be a cycloalkane. Notice I said it could very well be a cycloalkane, because there are some other compounds that could also meet that requirement. But definitely you know that that will not be an alkane. For it to be an alkane, it must be CnH2n plus 2. So keep that in mind. Okay, so now let us now continue with the nomenclature of cycloalkane. Okay, that's what we just told you. That is the general formula for cycloalkane. And cycloalkane, of course, are essentially compounds that contain carbon and hydrogen in a ring system. Okay. And all of the bonds are sigma bonds or single bonds. So when we get to nomenclature, we follow the same set of rules as we did when we did the alkanes. The difference here is that the base name must be the ring system. Say, for example, we take a look at this here. We have to name this to say, okay, how many carbon in the ring system? How many carbon? How many carbon in the ring system? 7. So therefore, the prefix cyclo, you just add cyclo, we call that prefix, cycloheptane, exactly. It becomes cycloheptane. So that becomes the base name for that molecule. And then, just as we did in the case of the alkanes, you then assign numbers to all of the substituents so that you assign the lowest possible combination of numbers to all of the substituents.
Okay, so
Okay, in this case, we start counting from here. 1, 2, 3, 4, 5, 6, 7. Okay? Okay, so now we have a branch in position 1, a branch in position 2, and a branch in position 4. And then you also follow the alphabetized in order. To name this becomes 2-ethyl 1,4-dimethyl cycloheptane. So all of the same rules that we gave you for alkane, you have to follow for cycloalkane. Yes. You want me to number it a different way? Is that what you say? Okay, let's try that. Let's try that. I'm not saying that is correct, but let's try it. Where do you want me to start numbering? No, no. You are in charge of the class now. Go ahead. At 4, okay. Let us use a green pen. So we start numbering from here. This is position number 1. This is 2. Is that right? Okay. This is 3, 4, 5, 6, 7. Okay. Okay, now, if you now what are the branches? Where are the branches? The branches are now in 1, 2, I'm sorry, yeah, 3 plus 3 plus 4. What is that? 8. Okay, so what do we have here? 2 plus 1 plus 4. What is that? 7. 7 is lower than 8, so that is why we have to use the lowest combination of numbers. Okay. Okay, so the correct nomenclature is 2-ethyl 1,4-dimethyl cycloheptane. All of the rules that we gave you for alkane, all of those rules you still have to follow. Now, if you only have one substituent on the cycloalkane molecule, then you don't need to indicate the number, because it just assumes that that is position number 1. In this case, what do we have? We simply have a methyl group attached to cycloheptane. So we simply call this methyl cycloheptane, which is what we have here. Okay? So you don't need to say one methyl, no. That is simply just assumed. Okay, another example, you have this here, bromocyclohexane. Okay? Now, sometimes when the branch has a longer carbon chain than the cyclic ring itself, then the cyclic ring becomes a branch. Okay, you follow that? Okay, let us take a look at this example here. Look at this, the alkyl branch has 4 carbons in there, but the ring only has 3 carbons. So in this case, now the ring becomes the branch. Okay, in that case, now you have to give the cycloalkyl name of the branch. Yes.
So why couldn't you just go like that? Not return it.
Oh no, you can't do that, because you're coming back here. If you have to take the ring by itself.
Oh, okay.
Yes.
What was stopping from counting from this way down? And
Counting from here?
No, the other side.
Where?
Like, because since the cyclopropyl is the branch, right? What would stop that from being a cyclopropyl butane?
Well, this is 4 carbon.
Yeah, that's what I'm saying. But like, you know how you have to count the carbons?
Mm-hmm.
Like, you're counting it from. You have to count it from left to right, or can you count it from right to left?
From here?
Yeah.
To here. Okay, but the point of attachment must be carbon number 1.
Okay.
Yes. The point of attachment must be carbon number 1. Okay. Yes. Okay. So in this case, the cycloalkyl branch, because you have 3 carbon atoms, if you have cyclo, remember cyclopropane, that would be the name of the cyclic molecule. Now, if you remove hydrogen from it, remember what we told you about forming alkyl group. You remove the A and E, you replace this YL, so it becomes cyclopropyl. Because in essence, this is what you have here. Okay, this is your cyclopropyl group right here. Okay, if for example you have this, okay, as an alkyl group, then what are we going to call this fragment? Cyclobutyl group, exactly. So this becomes cyclobutyl. Okay. So whenever the side chain has a longer carbon atom than the ring itself, then the ring becomes the substituent. So in this case, we name this compound 1-cyclopropyl butane because the cyclopropyl group, this here, is in the 1 position of butane. Because it is possible, for example, we could have this. Supposing we have this. What will you call that compound? What will you call that compound? 2-cyclo, exactly. 2-cyclopropyl butane. And what we are saying here is that the cyclopropyl group is in the 2 position of butane. Yes. Yes. Oh no, I'm sorry. That's it. Okay. You said the point of attachment? No, because if you look at this here, the base name will be a butane. So this is position number 1, position number 2, position number 3, position number 4. It's almost as though if I have this, supposing I have this, what will you call that compound? Becomes 3-methyl what? Hexane, exactly. 3-methyl hexane. Okay. So this is just another alkyl group attached to the 2 position of butane. Okay. 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 Just other some more examples of nomenclature. Now, in this case, if you have in this case, you have two alkyl group attached to this ring system here, which is cyclohexane, right? Just as we told you before, you have to assign the lowest possible number. So this becomes 1,3-dimethyl cyclohexane, and instead of, you do not say this, okay? Because you have to number so that you assign the lowest possible combination of numbers. Now, in some instances, it is possible that if you assign all of the numbers, if there are two different ways of assigning the numbers and both of them happen to give you the same combination of numbers, in that case, then you have to choose the alphabetizing order. Say, for example, look at this here. You have 1-bromo, 3-ethyl, 5-methyl cyclohexane. We could very well do this. What is stopping us from saying this is position number 1, 2, 3, 4, 5, 6? What is stopping us from doing that? Yes, but it will be the same combination. It will still be the same combination. Or even if you didn't do that, supposing you want to start the one from here, you could also say this is position number 1. No matter how you number them, they will all be the same. Exactly. So in that case, then the alphabetizing order will take over. Okay? So the bromine now assume the priority. Exactly. Okay? So now you go by alphabetical order. Bromine, ethyl, this. Okay? And that is why you have 1-bromo, 3-ethyl, 5-methyl cyclohexane. Yes.
So you have to go to the lowest number and
yes, and if the choices you have are essentially the same, then you look for the alphabetical order.
okay, so if it's two different numbers, you go on alphabetical order. So the numbers.
If the numbers are different, then you choose the lowest number.
Okay, but if the numbers are the same.
Right. Okay. And the same thing here. We have 1, 2. Oh, why can't you say this is position number 1 and this is position number 2? It will be the same combination, right? So in this case, you give the priority to the alphabet, which is ethyl as opposed to methyl. And so this becomes 1-ethyl, 2-methyl cyclopentane. What time do you have? Plenty of time. You know that. You know that already. Yes, go ahead. Which one? No. No, I was just saying that we could do. No, you cannot do that. But this has to be position number 1, based on the fact that ethyl, you go by alphabetical order. Ethyl comes before methyl. Okay, you follow that? Okay, how do you want to number it?
No, I'm saying that it's numbers.
Huh?
So we use numbers.
Okay, so anyway, in this case, if the two choices are the same, you've got to go by alphabetical order. If they are not the same, then you go for the lowest combination. In which case you add the numbers together. Huh? But you see, I have to name them, give the name in alphabetical order. Okay, what do you want to call it? No, you got to assign the lowest number to the alphabetizing priority. Yes. Okay. 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 Okay, these are just more examples of nomenclature. So, in this case, 1-bromo, 2-methyl cyclobutane. In this case, you see, I have to follow the alphabetizing order. Bromine comes before the methyl. Another example in which you have a choice of 1, 2, 3. So you have to start also using alphabetizing order. The chlorine comes before the rest of them. So 1, 2, 3. The same thing here. You have an ethyl and methyl. So 1 ethyl, 2 methyl cyclo pentane. Yes. Sometimes, just as in the case of the alkanes, sometimes you may have a complex branch. If you have a complex branch like this, okay, then we have, you place the name of the complex branch in parentheses, which is what we have here. 1-methyl propyl cyclobutane. Now, why do we call this 1-methyl propyl? This branch here. Okay, the propyl is in the 1 position of propyl group, right? Because this is your propyl group right here. This is your propyl group right here. So what we're saying here is that you have a methyl group in the 1 position of propyl. Alfredo, that's what you were asking earlier. Okay? And therefore, you then simply attach this complex group. You attach this to here. That's what we have here. Okay? In that case, the position of attachment must be carbon number 1. I think that was what you were asking me earlier. Okay. The position of the attachment of the branch must be assigned position number 1. Okay, so at this point we want to change here and go to slightly different concept. Yeah? Yes. 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 Now we want to we have two more topics before we leave. We want to discuss what we call, remember we gave you before constitutional isomers, right? You're laughing. Is that, no, what's the name again? That's not. It is? Oh, okay. Okay. Now let us discuss another set of isomerism. By the way, isomerism means existence of isomers. That's what it means. Existence or occurrence, existence of isomers or occurrence of isomers. Take a look at these 2 molecules here. Okay, we call this trans 1,2-dimethyl cyclopropane. See what we have here? We have the cyclopropane ring. Look at the cyclopropane ring. I'm sorry I did not bring my model. The cyclopropane ring essentially, or most of the rings are essentially flat, okay? At the bottom you have the methyl group coming to the bottom, and on top you have the methyl group coming on top. So in this case you say that is, those 2 methyl groups are trans to each other. So you call this trans 1,2-dimethyl cyclopropane because you show the 1,2 simply indicates the position of the branches. On the other hand, if you look at this here, we call this cis 1,2-dimethyl cyclopropane meaning that those two groups are on the same side of the ring. You see that they are both below or both above the ring. So therefore, these two molecules we refer to as cis-trans isomers. We refer to as cis-trans isomers. As we go on in, I believe, chapter 7 or so, we're going to find that these cis-trans isomers are one type of isomer we call stereoisomers. They are called stereoisomers. Stereoisomers because these are isomers that only differ as a result of the orientation of the atoms in space, or the groups in space. Okay. So we say the relationship between this molecule and this molecule here, we say this is cis-trans isomers to each other. Whereas this is cis and this is trans. You notice that the attachment of the atoms are the same, as opposed to in the constitutional isomers. Okay, say for example, supposing I have this. Oh, by the way, let me show this. Whenever you want to do represent the molecule in 3 dimensions, there are certain conventions that we use. Okay, let me do the 3-dimensional. Representation of organic molecules. Okay, I'm going to come back to this.
When you name this trend, is that going to be?
No, yeah, just a minute. If I have this, if I have a wedge, that wedge means that the bond is coming at you. Okay? Anytime you see a wedge, that means the bond is coming at you. Think of the regular line as being right here, right? And the wedge is coming right at you. And then we have the dotted line. That means the bond is going away from you. Okay? Okay, so for example, if I have a metal here and hydrogen here, what this is telling us is that this wedge is coming at you and this hydrogen is going away from you. Okay, so having said that, let us give you another example of cis-trans isomers. Yes.
When you're naming it, does this confer, like, let's say, if you go back to so that's come first, and then you name the...
Yeah. Okay. So if we have this, supposing I have this, and here okay, what will you call that molecule? How will you call it? What will be the name of that molecule? 1,3, exactly. 1,3 dimethyl. Okay, but before 1,3, what comes before 1,3? Cis, okay? Because the methyl group, okay, by the way, this would be hydrogen. This methyl group, they are on the same side of the ring. That's what that is telling me. Okay, so this becomes cis and hyphen 1,3 dimethyl. So then you follow the rest of the rules that we have been giving you. cyclohexane. Okay, so therefore the trans isomer will then look like this. Okay, so this becomes trans. This becomes trans hyphen 1,3-dimethyl cyclohexane. Now, supposing I give you this molecule here. Having said that, supposing I give you this here, okay, let us call this molecule A, molecule B, molecule C. What is the relationship between molecule A and molecule B? Would they be cis-trans isomers? Or would they be constitutional isomers? What is it? The relationship between A and B. No, the relationship between them? Are they cis-trans isomers? No, they are not. The attachment is different. A and C. Oh, did I say B? I'm sorry. I'm sorry. Yes. Now I gave that away, did I? Okay, sorry about that. It's between A and C. What is the relationship between A and C? They are constitutional isomers, not stereoisomers, not cis-trans isomers. Okay? Okay, very good. So you got that right. Okay, now about between B and C. What is it? Constitutional. Because the position, the attachments are different. Okay, keep in mind, all of these molecules here have the same molecular formula. Okay, for one thing, for you to say they are constitutional isomers or cis-trans isomers, they must have the same molecular formula because they are all isomers. Now, but A and B are what we call stereoisomers. Specifically, we call them cis-trans isomers. Whereas the relationship between B and C or A and C is constitutional isomers. Okay. So you need to recognize that. Okay, so I think we are almost at the end. Oh, we still got plenty of time. Okay. One more concept before we leave. Now we've done, you know enough about the cycloalkanes. Yes. Because the attachments are different. They cannot be cis-trans isomers because they are different attachments. Even though each one of them, these are all different compounds. Okay? But A and B are stereoisomers or what we call cis-trans isomers, whereas B and C are constitutional isomers. Okay, so the last thing we want to do today, let us now take a look at the reactions of alkanes and cycloalkanes. This will be very short. Now, because alkanes and cycloalkanes, all they have are sigma bonds, they are not very reactive. But however, they do undergo certain reactions. And this type of reaction is what we call free radical. Today we are simply just going to show you the reactions, and in subsequent chapter we will show you the mechanism of this reaction. In other words, how do this reaction take place? But today let us simply content ourselves with simply knowing what the reactions are. If I have this methane, I could react methane with chlorine in the presence of light, that is light, or heat. I will replace one of the hydrogen with a chlorine. Of course, hydrogen chloride is formed. Believe it or not, this is the same type of reaction that takes place in your swimming pool. You know, there's a lot of hydrocarbon in the swimming pool water, methane, butane, all those stuff. And then they use chlorine to treat the water, right? The chlorine in the presence of sunlight, you get this type of reaction taking place all the time. Okay, so this is what we call halogenation of alkane. This type of reaction we refer to as halogenation. Of alkanes or cycloalkanes. The same reaction we could get if, for example, we take cyclohexane, we could react with bromine or chlorine in the presence of light. We also will get bromocyclohexane plus hydrogen bromide. Now, each one of these here, we refer to this as a monochloro product. Monochloro product. Or in this case, this would be monobromo product, right here. We say monobromo product or monochloro product because only one of the hydrogen has been replaced by the chlorine. Because this reaction could continue. The chlorine could come back here and replace this other hydrogen, and those reactions will continue. Other examples. If I have this, chlorine in the presence of light, what do we get? How many monochloro products do you think we're going to get? One. Because no matter if you replace any one of these hydrogen, they are all equivalent. The product you get will be the same compound. Okay, so therefore, Okay, so you get this monochloro product. Because in this case, all of these hydrogens, they are all equivalent hydrogens. If you replace one of the hydrogens, it doesn't really matter. You're getting the same product. Okay. So most of the reactions of alkanes essentially we deal with free radical reaction, which will be halogenation, just as we show you here. Some other type of reaction, of course, is combustion. You know that your gasoline is mostly made up of alkanes and other hydrocarbons, so you get some combustion. But as far as the organic chemistry is concerned, the halogenation reaction is very, very important. Yes.
There's something that you want to do that is something like arrows and something else that are particular
What?
You need a lumen structure.
To do what? A lumen? Oh, Newman, yeah, yes. No, no, I know. I said, no, we will do that. We are not going to do that this time. Newman. Yeah, no, well, don't forget that you are. Okay, no, don't forget. I know. How many questions? 4. Yeah, I will take them. I'll take them out. Don't worry. No, I can't take them out. I can't take them out. But don't forget that for you to get a maximum, to get your maximum score, all you need is 80%, right? To get 80%, right? Don't do those for now. Do not do those problems. Don't do them. Okay. Okay. Anyway. Yes. Any other questions? Okay, folks. We have finished for the most part chapters 3 and 4. The only topics that we need to cover in chapter 3 and 4 will be the Newman projections and the conformation, and so we will do those in the next exam, not in this exam.
Are you considering
What?
my ideas?
I will see you guys on Monday during the online session.